SPP on the Y. Of course, you have to solve the Bessel function equation for this to get SPP. Not that simple Fresnel reflection coefficient. You have to go through chapter, is it chapter 3? Yeah, chapter 3 of my book, right? Solve the cylindrical coordinate problem. Look for those guided modes. And you'll find those modes. And you'll find that the mode profile will look something like this, which is wonderful because the confinement is really good compared to optical fiber. The only problem that people face now is the loss. Okay, we have this goal, we have this servo. We have extremely good confinement, but it doesn't propagate very far because of the loss that we have. Okay? Any questions on this SPP? If not, we move on to something else. We move to a simple model of nanoparticles. A very simple spherical model of nanoparticles. And explain why all that glitter is not gold. Okay. So we can do the case of a sphere very easily because we can obtain closed form solutions for a sphere. And when we excite a spherical nanoparticle with an electric field, I might have these two reversed, I'm afraid. This might be in gold, this might be in air. Okay, I will go back and check. Because I don't recall what is epsilon 1 and epsilon 2. And when they look at this again, they put epsilon 1 in here, epsilon 2 out there. This is air, this is gold. Okay, so I might have the other two reversed. So if I have this spherical nanoparticle, if I want to excite it with an electric field, this is region 1, this is region 2, and if there's an electric field coming in, and this is on the order of say 10 nanometers, it's much smaller than wavelength, so small that I can use quasi-static electromagnetic theory to analyze this problem. Ask myself, in the long wavelength limit, what is the solution to this problem? So I can solve Laplace equation instead of Maxwell's equation in this full glory. I know that the potential in region 1, which is inside the sphere, has to be something of this form. Potential has to be something of this form because the field E1 is minus grad phi1. It's just minus B, right? So BZ hat. So the field is a constant inside the sphere because the sphere is so small. It turns out that in fact the constant solution exists inside this sphere. And then just outside the sphere, I have another solution. I can write this in polar coordinate system. So that gives me that thing over there. And then the potential in region 2, I can write the incident field. Incident field can be written in this manner, plus the response from the particle. The response from the particle is just given by this formula over here. This is the potential of a dipolar field. And I can write the incident field as just r cosine theta plus a cubed over r squared cosine theta. Okay. So this is incident. Incident field or the incident potential. And if you take the gradient of this, you just get E incident is equal to E naught C hat. You take the gradient of this, the negative gradient of this gives you this as the incident. So I'm studying the excitation of this particle with a long wavelength electromagnetic field. So I can assume quasi-static physics there. Now I match boundary condition. I match boundary condition that potential must be continuous. If I enforce the fact that this must be continuous at r equals a. Okay, on the surface of the particle, r equals a. If I enforce that potential must be continuous, I get this very simple equation: B A, cosine theta cancel all throughout, must be equal to minus E0A plus A. If I let R be equal to A, this is just AA. So I have this very simple equation to begin with. And what is the next boundary condition that I should impose on the surface of the conical? I have two unknowns, unknown 1, unknown 2. What is the next? This is the undergraduate freshman physics or EM 101, right? If you forgot your EM 101, you will not know how to find the second boundary condition. If you remember your EM 101, you should know what the second boundary condition should be. What should it be? Aditya, what do you think? Neumann? Is it Neumann? Yeah, somewhat similar to Neumann, but what is it precisely? Neumann is what the mathematician will speak.
The normal derivative is continuous.
Yeah, but not precisely. What is it that you should impose on the surface of the particle? If you speak electrical engineering or electromagnetics. Mike should know, right?
Is it normal D?
Normal flux should be continuous.
Yeah.
Normal D should be continuous. And that follows from the fact that divergence of D has to be 0. This equation implies n dot D continuous. I taught you how to eyeball boundary conditions from the equation. You just need to look at this equation. You know that should be the boundary condition. Okay. And you should be able to eyeball boundary condition by just looking at the equation. Okay, so if you impose this boundary condition, then the normal D is by taking the normal derivative of this and multiply by epsilon 1 in this case and epsilon 2 in that case. And then if you do that, then you get B epsilon 1 must be equal to epsilon 2. Okay, you multiply by the appropriate boundary condition, and I can solve it for you, okay? I don't want to go through the detailed algebra. I can find what A is. A is epsilon 1 minus epsilon 2 over epsilon 1 plus 2 epsilon 2 E naught. B is minus 3 epsilon 2 over epsilon 1 plus 2 epsilon 2 E naught. So they are linearly proportional to the exciting field. But what do you notice about A? What could happen to the denominator of A if you have a gold nanoparticle? What could happen to the denominator of the expression A? You can go to 0, right? And then you can hit the resonance. So this is actually fantastic. This is actually fantastic. You have a particle so small and yet it can resonate. Isn't that wonderful? Because as a microwave engineer, you will think that I have to make something on the order of wavelength or half a wavelength in order to make it resonate. But this is an occasion, a situation where this particle is sub-wavelength and yet it resonates. It resonates when the denominator vanishes. Because epsilon 1 can be negative. And you pick a frequency. Epsilon 1, again, as I said before, using a very simple plasmonic model. Okay, so change the frequency, you can get epsilon 1 to be exactly equal to the negative 2 epsilon 2. And it only happens at a particular frequency. It does not happen at all frequencies that this goes to 0. So this is like a resonance. Like the resonance of an LC tank circuit. So you can think of this as like the resonance of an LC tank circuit. Okay, so this is another situation where you can make a resonator that is sub-wavelength. The resonator is very small here. You can make the inductor very small. capacitor very small, and yet you can have a small resonance. So what is the similarity in the physics here to that of the LC10 circuit? Why can that thing resonate at such a long wavelength? Do you know why that it resonates at such a long wavelength? Where does the negative epsilon come from? It comes from the inertia of the electrons. So you can think of, if this is a plasmonic particle, it has a lot of electrons in there freely moving about. Those electrons have inertia. They are reluctant to be moved unless you apply an electric field. So the reluctance to move about is an inertia that behaves like an inductor. An inductor has that reluctance to move about too. When you try to force current through an inductor, it refuses to let current go through. So that inductor is actually very similar to those electrons in there. So you can think of this as a kinetic inductor. So when you hear the word kinetic inductance, occasionally when you go to conferences and people talk about kinetic inductance, they're referring to this kind of physics. That is inertial term. The inertial term actually contributes to the negative epsilon. A negative epsilon contributes to a negative capacitor. Okay, does that sound familiar? Negative capacitor is actually similar to an inductor, right? Because we have this thing, J omega L, this is Z, Y is J omega C. So if you take the reciprocal of this, a negative capacitance is the same as a positive inductor. So when epsilon turns negative there, you can think of that I have a negative capacitor. Actually, it's similar to a positive inductor. So I actually have a kinetic inductor working for me, and it starts to resonate. There's one picture that you can take. Another picture you can take is that there's a lot of kinetic energy in the electrons, in the nanoparticle. Those electrons have inertia, and then when you try to move them around, the kinetic energy is being exchanged with the electric field energy outside. You have E field outside the closed. You have a lot of stored electric field energy outside. And to have any oscillating system, to have any resonant system, there has to be exchange of two energies. Exchange of stored energy in the electric field with the stored kinetic energy in the electrons. Those two are exchanging between themselves. Like a swing in the park. Look at a swing, you exchange potential and kinetic energy. You go to the inductor, you exchange stored magnetic field and stored electric field. But in this case, it's not stored magnetic field, it's stored energy in the kinetic energy of the electrons. Okay? And that stored energy is being exchanged with the stored energy outside, and it starts to have this plasmonic resonance also. And then that's why gold particle glitters more than it does compared to when it is in bulk, in small nanoparticles. They have this glisten to them that I guess the Romans found out about 10 years ago, 2,000 or 3,000 years ago. I don't know when the Romans found out about that. They started to make this chalice and then put more nanoparticles into them, and then you get this brilliance of color. And you see this in the news, you see this in Wire. And some professors are claiming that what they do now is actually related to the work of art in the church, in the Hinton class, you see in the church that was done 1,000 years ago. People found this phenomenon years ago, and now they start to understand why that is the case. Okay, I guess I'll stop here.